Hello everyone. Today's topic is basics of design and we are going to talk about introduction to CAS and classes surfaces. In today's topic we are going to cover what are CAS surfaces or digital plane models, why CAS surfaces, what are classes surfaces, role of a classes surface engineer, requirements of a class surface to fulfill class A surface standard and why class A, and we'll have a case study of a class A surfaces. You'll also see a step-by-step process of bonnet classes surface creation. In the end of this session, we'll be able to explain what are CAS surfaces, define class A surface, explain importance of class A surfaces, list requirements for class A surfaces, list the steps of bonnet class A creation. Now, what are CAS surfaces? Uh, in my other sessions, I have talked about CAS surfaces and class A surfaces a lot. Now we're going to see that what exactly they mean and why they are important. CAS surfaces can be defined as initial low-quality surfaces made from sketches or clay wood scans for overall aesthetic visualization and feel or form of a surface shape. Basically, CAS surfaces are very low-quality surfaces. They are like very rapid surfaces, what we make from sketches directly. We interpret sketches and we directly put them on a 3D model and we make some models out of it. Or we can have some scan reference from a clay or a wood model and we develop surfaces from that. In simple, CAS surfaces are computerized aided styled surfaces, and their main role is to basically define the aesthetic appeal of the product and give a more uh, visual and more of for visualization rather than any production quality. They are the first level surfaces what we create from sketches so that the designer can understand how in 3D they look like, how his sketches and the 3D model or the actual car is going to relate together. So that's the main reason why we make CAS surfaces. And why we do CAS surfaces? Because physical models are very expensive. In earlier time, when there was no computers or we don't have computer aid, every time every theme has to be actually put on a clay or a wood model, and a person has to really work on it to give the real 3D form of it. It's a very long process time. It's long. There's a lot of time. It takes a lot of time to make an actual physical model, and it's expensive also. And above all, you have very limited themes what you can make because it's expensive, it takes a lot of time. So you are limited by the number of themes. You can go only with one or two themes because of the other factors. And once one model is made, once one physical model is made, you cannot keep on changing that. There is a limit to that. You can only do few changes in it, and it's limited by its size and limited by its the amount of material it has. So these were the reasons why CAS model, or when we had computers and we started developing models on it, it took up really well. From a 10 to 12 years development time, we have cut down to almost like 2 years development time now. And this is all because of the computer aid what we have. And we can now with the technologies like 3D experience and all that, we can actually see the car in a real 3D form even without making a physical model. So these are the advantages of CAS surfaces. But in the end, we cannot use these CAS surfaces for production because the idea is to bring out the design intent and the aesthetic feel of it. It's not for production. There are a lot of problems in the surface in terms of quality. That's why they are limited to this use only. To overcome that and to actually build production quality surfaces which can be used for production and which ultimately goes to engineering where they can engineer the model, we have to increase the quality of the surfaces. We have to really kind of add a lot of value to the surfaces, and that next stage of surfacing is called as classy surfacing. In simple words, a class A surface are those aesthetic freeform surfaces which are visible to us and having an optimal aesthetic shape and high surface quality. So this is very opposite to CAS surfaces. CAS surfaces are aesthetic surfaces with very inferior quality, whereas these are also aesthetic surfaces which are visible to us and they have a very optimal and high surface quality. Now there is one term which is very wrongly used in industry is A surface and class A surface. There is a confusion in that. All the surfaces what we can see by our eye is known as A surface, but they are not class A surface. For class A surface, these have to have a very high quality requirements, and if they have all those high quality parameters in them, then we can term them as class A surface. So mathematically, a class A surface can be defined to have a simplest order of surfaces joined together having a high degree of position, tangent, and curvature continuity. Now, these are some of the mathematical parameters how you can define what class A surfaces are. Or in other words, you can say class A surfaces are those which have a high gradual rate of change of curvature across the surfaces. So, saying all that, in short or in very simple words, class A surfaces are the visual surfaces what we can see in the car or outside the car, and they have the highest quality of uh, highest surface quality and highest aesthetic appeal. You can make out the difference between a class A surface and a non-class A surface the moment you look at it. I give you an example. Look at the bonnet, the fender, bumpers, and all these parts of car. These are class A surfaces. The moment you lift up the bonnet and see the interior of the car, those are not class A surfaces. The idea of those surfaces are not to provide aesthetic appeal, but to add rigidity to the car. So this is the main difference between the class A surface and class A surfaces and non-class A surfaces. Now, what is the role of a class A surface engineer? A class A surface engineer is more like a negotiator. He has to respect and transform a designer's idea into a production reality. He has to negotiate between what designer wants and what engineering requires. So it's always a conflict between the two because designer always wants something very different, very out of the world, which engineering generally doesn't have seen it or they have certain constraints on it. A class A surface engineer is a kind of a negotiator between the two. He has to make something what really a designer wants. He wants in his design, the intent, the lines, everything has to be as per what design theme is. At the same time, it has to surpass or it has to, fulfill the criteria of engineering. It has to be wrinkle free. It has to have all the draft values into it, the texture condition into it. So all these things are to be there in those surfaces. So that's the role of a class A surface engineer. Now, these are the certain requirements of a surface to fulfill a class A standard. As I said earlier also, there are visual characteristics, mathematical requirements, and manufacturing requirements. These are three areas a class A surface has to uh, fulfill all the requirements. In visual characteristics, it has to have all the aesthetic requirements what designer wants, reflection, smoothness, and all the style feature what designer needs. Mathematically, it has to be position, tangent, curvature, and torsion continuous. And from the manufacturing point of view, things like the panel should retain their shape and the feature lines should retain their shape. All the wrinkles are not there. Uh, uh, the manufacturability of the form and shape is to be taken into account. These are the things which a class A surface engineer has to see, and he has to put all those into those surfaces. Now, why we need a class A surface? That's a big question. Uh, as I said earlier, these are high quality surfaces. So why we need a high quality surface? Because in today's time, great product is something which you see and buy. It's not something, it's because we are selling that you are buying it. Customer is quite choosy and it makes the appeal of a product makes a big difference in its sales numbers. So if you have a high quality surfaces, if you have a very aesthetically pleasing form and form, etc., the chances of selling that product is way higher than a similar product with not such a great appeal. Classy surfaces or a good quality surface or a good form creates something what we call it as desire. The moment you look at it, you feel like, oh, this is good, let's buy it. Let's take an example of a high-end cars like Mercedes, BMW, and Lamborghini. Uh, the moment you look at it, you have a desire of owning that car. You may or may not buy it, but you have that desire. Why? Because the moment you look at the form, it gives a sense of, it gives an expression that it's very fast. It's very the form itself says it's very like if you look at Lamborghini, it directly tells you that I'm a fast product, I'm a very high speed product, and I'm very manly also. So these kind of things, these kind of uh, uh, the overall shape of the car, overall what you appeal, what you see, it's directly reproduced by the quality of the surfaces and the overall quality of the form. And overall quality of the form can be achieved by high quality surfaces. Classy surfaces also gives a very good perceived quality feel. The streamline and reflections can give you altogether a different appeal of a product, like as I said in Porsches and Lamborghinis, what you see. So that's the reason we need classy surfaces to actually enhance the form of the product and to make it more sellable. Now, there is some case study of a classy surface of what is good, what is bad, and all that. If you see the surfaces at the top and the bottom, they look very similar. There's not much a difference between the two. But the moment we describe it from a classy perspective, there's a hell lot of difference between the two. The top one, if you see the CV distribution and batch optimization, it's very high. There are only 4 CVs in both the directions. And the bottom one, you see all the jagged up. But still, the surface looks similar. But there is a great difference between the highlights of the two. And the last, you can see the lines look very same, but mathematically they are not center symmetric. So when this product will be actually produced, you will see a very hard line between the two joints. So these all can be removed. Even the difference is very minimal. It's in millimeters, it's 1/10 of a millimeter or something like that. But it makes a very big difference when the actual product is produced. Now we will see a step-by-step process for a bonnet creation and how we start from ideated sketches to ultimate a classy surface. As I said in my previous slide, in previous presentations also, everything starts from sketches, then we make scale models, then we make one-to-one scale models, and in the meantime we make cast models and all that. So here I'm explaining the process if we have a scale model or a full scale model and we take a scan data of that. So we have a scan data, it's a point cloud data. A point cloud data is basically it can be captured by a white light scanning or laser scanning. It's nothing, it's a clutter of points in a very defined position, and that's why we call it as a scan or a point cloud data. Once we have that, we have to go through certain processes to actually make it usable. So one of that process is scan filtering. We have to filter out non-usable points. We have to remove that and we get something more usable scan data. We remove all the spikes, unwanted areas, and we get a finally usable surfaces. And that process we call as scan filtering. Once we have a filtered data, we go to the next process, what we call it as polygonization. Now, polygonization is nothing but it's a visual representation of a point cloud data in a surface form. All the points are linked by all the adjoining 3 points are linked by a surface, and this is how we create a kind of a, STL data or polygon mesh, and we call it as a polygonized data. Once we have that, we go to the next step, what we call it as a sectioning or map data. Now, map data is a commonly used term across the industry because previously in olden times we don't used to have white light scanning, and everything used to be scanned by a CMM. So we used to get always cross sections. But this process is still used, and we have sections of scan data, and this we take it to make the surface data. From here, we start making curves, and we start plotting what feature wise what curves lie where, and we start building a curve network of it. Once we have the curve network, from that we can build a surface network of that, and we regularly check certain quality parameters in that, like deviation and curvature continuities and all that, so that it bites all the class A norms. Once we have the surfaces, we do certain diagnosis like overlap. We see that what is the difference between the cloud data and the surface data what we created. If we can see that it's very much in matching, and then we do deviation check. You can see it's very much matching to the cloud data, and then we do certain curvature checks, and finally a highlight check and all that. And once all these diagnoses are okay, this data can be released as a production surface or a class surface. So in the end, what we understood in this session, that what are CAS surfaces, what are classes surfaces and its importance, and what are the requirements of a classes surfaces. Thank you.